gotta go over card problems,
Oh, great.
which are interesting but not easy.
I feel like how would the triangle table method or whatever it's called?
That's Monday's lecture.
What's the preference?
Banquet table.
You mean the prom problem?
Something like that, yeah.
The prom?
Yeah. Well, you're gonna get this problem on the test. How many ways can 5 couples be seated around a circular table?
Oh.
If each couple got to sit together, isn't that what you do at the prom?
Oh.
Unless you're weird.
Go.
Well, no. Well, that's Monday's lecture.
Wait, is this the chapter? Do we also do that thing where you said that it's like the probability that someone's birthday is?
No, that's the next chapter. We're learning how to count now.
You know what
And
I'm
then
talking
the next chapter is probability.
You know what I'm talking about?
Did somebody steal the worksheets? Nobody stole them, did they? Takagi!
Yeah.
Where's the worksheets? I was just looking at them.
It's okay.
No, it's not okay. Did I bring them over here? Am I?
So I feel like it waits.
It's not here.
I'm surprised you
Somebody
just-
took them. I know it's somebody's not admitting it. Morris?
Nope.
Oh, you know what I should do? I should hold my iPad then, yeah?
Yes. Yes, you should.
Stop telling me what to do. Yeah, I'll hold the iPad. Great. Okay, how does this work? We have to go to Google Drive. Where's Google Drive?
Oh, we're on Google Drive? That was just on the website.
No, but I have to put it on Google Drive before I can put it on the website. Something about the sharing thing.
Yes.
Isn't it easier just to go to the website though, if you just want to look at it?
But if Google Drive's already loaded.
What are we doing?
Google
We're
Drive.
doing combinatorics now.
Two.
For one.
So
Combinatorics,
just press
two.
it.
Uh-huh.
3.
Two.
There it is.
4.
Two.
5.
Stop
Okay,
trying to
and
trick
then
me.
just go.
Two.
Okay, there we go. No, that's the examples. Hold on. Got 3 pages of examples. How can you not do this? Okay, 2B.
Wait, I wrote B.
How many 3
That was me.
Okay.
Okay, this problem is definitely on the quiz on Monday. 2A. What about 2A?
Yeah, that's what I said.
Okay. 2A is easy.
Well, it's not.
1, 2, 3. How many 3-digit even whole numbers can be formed using the digits 0, 1, 2, 3, 4, 5 if repetitions are allowed? Now, if this is going to be an even number, how many choices do you have for this last digit? 3, because it's either the 0, the 2, or the 4, right?
Yeah.
How many choices do you have for the first digit? Anything except 0, so there's 5. How many choices for the second? 6. Anything, so 6. Done. Because you can use 0 as a second digit. Okay, but now, here, wait, what's happening? Okay, now, how many, if repetitions are not allowed? So, see now, a lot of you have probably did this, yeah? If you attempted the homework, you go, okay, there's 3 choices for the last digit, right? How many choices do I have for the first digit now? For those of you who actually did the homework. Well, doesn't it depend? No, doesn't it depend? Yeah, it depends on whether you pick the 0 or not, right? Because if you pick the 0, then you would have 5 choices for the first digit. But if you didn't pick the 0, like you picked the 2, then you only have 4 choices for the first digit. You know what I'm talking about? The 0 is a problem. So, what you gotta do is you gotta make 2 cases. And what are the 2 cases? The first case is 0 is the last digit, or either the 2 or the 4 is the last digit. You gotta remember this, otherwise you can. Okay, so if 0 is the last digit, let's say you use, how many choices do I have for the first digit? 5 and then 4, because there's no repetition. Okay, you multiply that, you get 20. What if 2 or the 4 is the last digit? You have 2 choices, right? Either the 2 or the 4. Now let's suppose you use the 2. How many choices do you have for the first digit?
5.
No, you cannot have 0 as the first digit. You guys gonna make this simple mistake on Monday? 0 cannot be the first digit of a number. You have 4 choices. Let's say you pick the 4. How many choices do you have for the second digit? 4, because now you can use the 0. 0 cannot be the first digit, but it can be the second. You guys get it? So 4, multiply it, and you get what? 32. And then what do I do with these two numbers? You add them because these are two mutually exclusive cases, so that's 52. Or, what's another way you could have done this problem?
Cases for the first one.
What, girlfriend? No, you do the complement. What's the complement of a 3-digit even number? 3-digit odd number. So, odd number. Now, if this is going to be an odd number, then how many choices do I have for the last digit? 3. Let's say I pick the 3. How many choices do I have for the first digit now? Oh, 0 cannot be the first digit. You guys are killing me. Okay, look. If you pick, what did I say? 3. How many choices do you have for the first digit?
4.
You have 4. You cannot pick the 0, that's why. Let's say you pick the 2. How many choices do you have for the second digit? 4, because now you can pick the 0. Then you multiply it out. What is 16 times 3? 48. And then you subtract that from the total. How many total 3-digit numbers can you make where there are no repetitions? How many choices do I have for the first digit? 5. 5, and then 4, because 0 can be the second digit. You multiply that out, that's 100, and then you subtract it from the total, 52, you still get the same answer. In fact, this is how you can double check to make sure you get the problem correct. But I don't think anybody's going to do that yet. Are you going to remember to make the 2 cases then on Monday? No. Okay, then you get this problem wrong. Okay, 5, 6, 9, 10. Number 5. How come there's so little bit people in this one? They get excused this early?
12. They're in. It's not like.
No way baseball gets excused this early.
Yeah, Brandon's not here.
Well, because they got to take a nap and eat a meal, yeah? Or is that just football? Okay, how many ways can 2 admirals, 3 generals, 4, I think this problem's on the quiz too, except I changed it to birds, cats, and dogs. Is that going to throw you off?
No.
Yep.
What if I make mathematicians, scientists, and what's another category? Okay, whatever. 9 seats. 1, 2, 3, 4, 5, 6, 7, 8, 9. If a general has to be at each end and the diplomats are in consecutive seats. So, if this has to be a general and a general, how many choices do I have? 3, and then 2. And then the diplomats must sit together. So, do a specific case. What if the diplomats sit in these 4 seats right there? How many choices do I have? 4, 3, 2, 1, because it's got 4 diplomats. There's 3 people remaining. It doesn't matter what they are. So how many choices do I have for these 3? 3, 2, 1, because they're just 3 people. It doesn't matter what they are, diplomats, generals, whatever. So this is the case where the diplomats are sitting in these 4 seats. But are there other cases where they have to be clustered together? Yes, they could have been sitting in these 4. What about those 4? What about those 4? What about those 4? So how many cases is that? 4. So then you got to multiply by 4. So you write that down on your paper, you get 3 out of 4 points. You want the 4th point, you got to compute that. Which is way less than 10 million, right? Okay, I'll make a deal then. It'll be less than 1 million. Unless I make a mistake. 6. How many ways can 4 math? That's the same thing. See, get books instead of people and then you're thrown off. 4 math books, 3 science books, and 2 history books be arranged on a shelf so that the books from each subject are clustered together. 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's do a specific case. Here are the math books, these are the science books, and those are the history books. So math, science, history. So how many choices do I have for the math books? 4, 3, 2, 1. What about the science books? 3, 2, 1. 2, 1. But this is just the case where the math books are first, the science comes second, and the history is third. Are there other cases? So it's basically, it's like, I have 3 things. How many ways can three things be arranged in a row? 3 factorial, right, which is 6, so the multiplication factor is 6 then. See, you do a specific case, and then you multiply by the number of cases. But this takes practice, people. You think you can just watch me do it in the morning, you're gonna come through on Monday. Kobe's saying yes. It hasn't worked so far, did it? No, I'm saying, never mind. Number 9, using the letters in the word logarithm. How many letters are there? 3, 6, 9, there's 10. How many 3-letter words containing exactly one vowel can be formed if each letter is used at most once? So we're making a 3-letter word, and it has to contain one vowel. Okay, let's do a specific case. What if the vowel is here? How many choices do I have? 3, and then this is a consonant. So how many choices do I have? 6, and then you cannot repeat, so 5. But that's just the case where the vowel is in position 1. Are there other cases? Yeah, the vowel could have been in position 2, could have been in position 3, so how many cases is that? 3. So you multiply by 3. Yeah, it's kind of easy. And then number 10. How many ways can 4 people be? Okay, there's an easy way and there's a hard way. Let's look at the hard way first, because you guys probably did it this way. Huh? Okay, number 10. We got 9 chairs. 1, 2, 3, 4, 5, 6, 7, 8, 9. How many ways can I seat 4 people into these 9 chairs? Okay, let's do a specific case. Let's say the 4 people are seated in seats 1, 2, 3, and 4. How many choices do I have? 4, 3, 2, 1. Okay, but that's just the case when the people are sitting in seats 1, 2, 3, 4. How many cases are there? Anybody? Well, let's write it out. They can sit in seats 1, 2, 3, 4, 1, 2, 3, 5, 1, 2, 3, 6, 1, 2, 3, 7, 1, 2, 3, 8, 1, 2, 3, 9, 1, 2, oh, that's not 1, 1, 2, 4, 5, 1, 2, 4, 6, 1, 2, 4, 7, and you just keep on writing them all out until you get to 6, 7, 8, 9. That's how many cases there are. Anybody? Come on, somebody impress me.
9 factorial.
No. Somebody?
9 factorial over, it's 9c4.
Ooh, very good. Not Davis. That's right, but we never even learned C yet. That's today's lesson.
That's the one. I did not do it.
Okay, so anyway, you would have to count all of this, and I think there's like, how many cases then? 4, 3, 2, 1, 9, 8, 7, 6. 126 cases. So you multiply by 126. How many of you can count that many cases? That's too difficult. That's too difficult. Here's an easier way. Instead of making the slots for the chairs, make the slots for the people. Okay, there's 9 chairs all in a row. Here's the first person, comes up. How many choices does that first person have? 9. Now that person takes one of the chairs, so the second person comes. How many choices does he have? 8. And then? 7. Wait. And then how many choices? 6. Boom, there's your answer. See, so instead of making the slots for the chairs, you make the slots for the people. I can tell you don't like that one. Okay, and is that it? Because we did the permutation lock yesterday, yeah? I think we might see that one too. So out of these 12 problems right here, 5 of them are on Monday's quiz. I just changed some numbers around.
Which 5?
I'm not going to tell you which 5. I'm not going to tell you. Why should I tell you? This is honors, you know. I thought it was honors. Okay, so last night's homework was permutations. Now we're going to do combinations. Somebody stole my worksheets. I want to know who it is. You didn't get a video, keep the video on? Well, there it is.
See, you stole your own worksheets.
Okay, nobody stole it. Okay, today we gotta learn about combinations now. So what happens when the order is not important? Then it's called a combination. Now we already talked about this because you remember when we did the binomial theorem, I had to teach you about combinations? So let's review. So like if you have, think of something where the order is not important. Suppose you have 9 candy bars and you want to put 4 of them in your lunchbox. These are all different candy bars, by the way, yeah? You have 4 of, and you want to select 4 of them to put in your lunchbox. How many ways can you select them? What, does the order matter? No. So it's a combination, it's like a committee of people, right? It doesn't matter who's first, second, or third, or fourth. So the answer is going to be 9C4. It's the combination of 9 things taken 4 at a time. Or, we write it like this. Both of these mean the same thing. It's the combination of 9 things taken 4 at a time. Or you can just say 9 choose 4. I think this is the way I taught you, yeah? Now, you guys remember the formula to compute this? NCR is equal to n factorial over r factorial n minus r factorial. Hey, Mr. Park, that looks like the permutation formula. It is, except we divide by an extra r factorial. Maybe you can tell me why next week, after you go through some of these. So, how do you compute 9 choose 4? You use this formula, but remember I taught you the shortcut because things cancel out. I mean, you can use the formula, but there's a shortcut. Do you guys remember what the shortcut is? You put 4, 3, 2, 1 in the bottom, 4 factorial in the bottom, and then starting with 9, you just match the number of numbers. You have 4 numbers on the bottom, you just put 4 numbers on the top. Because the other stuff is going to cancel out, the 5 factorials. Does that sound familiar? Okay, let's use the formula then, okay? So if you use the formula, you're going to have 9 factorial all over 4 factorial. 9 minus 4 is 5 factorial. Okay, what is 9 factorial? 9, 8, 7, 6, 5, 4, 3, 2, 1. What is 4 factorial? 4, 3, 2, 1. What is 5 factorial? 5, 4, 3, 2, 1. Can you see that these are going to cancel out? So then just write that, which I did. And so, let the canceling begin. 4 times 2 is 8. 3 goes in 6 2 times. So we got 14 times 9, 126. Comes from the last problem, if you guys didn't figure it out. So there's 126 ways you could have selected 4 candy bars from 9 to put in your lunchbox. Okay, what if you had 10 candy bars and you want to select 7 of them to put in your lunchbox? How many ways can you do that? 10 choose 7. But what did we learn in second quarter? 10 choose 7 is the same thing as 10 choose 3. Why? Because the formula. Plus remember Pascal's triangle is like this? That's symmetric. You guys didn't remember Pascal's triangle? 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. What do we use these numbers for?
That's squaring.
No, raising a binomial to a power. These are the coefficients. And remember, in the 4th rule of Pascal's triangle, these numbers are 4 choose 0, okay, 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. Does that sound familiar? That's why these two got to be the same, these two got to be the same, and that is symmetric. Anyway, why is it better to compute 10 choose 3 than 10 choose 7 if they're the same? Because you want the smaller number on the bottom if you're going to use the shortcut, because then you just go 3, 2, 1 under 10, 9, 8. Or would you rather go 7, 6, 5, 4, 3, 2, 1 under 10, 9, 8, 7, 6, 5, 4. Same thing, because look, get it's the same thing. Anyway, let the canceling begin. Da 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 3, 4, 12 times 10, 120. So there's 120 ways you can select 7 candy bars from 10 to put in your lunchbox. Yeah, which is the same thing as selecting 3 candy bars from 10. Okay, you guys think you're good, yeah? Okay, let's kick it up a notch. Okay, suppose we have 7 girls and 6 boys. Now maybe we better make the number smaller for you guys, yeah? Suppose we have 5 girls
3 boys.
and 4 boys. I want to make a committee of
4.
of 5 people. Now, once you see the word committee, you got to be thinking this is a combination, right? Because the order doesn't matter. Okay, how many committees of 5 people can I make? Yeah, the answer is just 9, choose 5. Out of these 9 people, how many ways can I select 5 of them? And then easy. That's the same thing as 9, choose 4. So you go 4, 3, 2, 1, under 9, 8, 7, 6. Let the canceling begin. 2, 2, 2, 2, 2, 2, 2, 2. Hey, that's the same thing again, 126. Okay, but now let's put some restrictions on it. How many committees of 5 people can you make that have 3 girls and 2 boys? Because you want to have more girls than boys because you want to get something done, right? You don't just sit around playing video games all day, right? Okay, so I want to select 3 girls from the 5. How many ways can I do that? 5, choose 3. I want to select 2 boys from the 4. How many ways can that be done? 4, choose 2. Now the question is, what do I do with these numbers? Do you multiply them or add them? Why? Because they're close together. If the things are close together, you multiply. If they're far apart, you add. No, the real reason is because these are occurring together on the committee at the same time, right? You have 3 girls and 2 boys. The word "and" kind of implies you multiply, and the word "or" implies that you're going to add. And then now we can compute this. Now, let's see if we can do this in hand. These numbers are small enough. 5 choose 3 is the same thing as 5 choose 2, which is 5 times 4 over 2 times 1. Yeah. 4 choose 2 is 4 times 3 over 2 times 1. It's 6. So there's 60 different committees you can make here. Okay, now, how many committees of 5 people can I make that contain at least 3 girls? Because again, you want to get something done, right? So what does at least 3 girls mean?
3 girls.
You could have 3 girls. What are the cases? 3 girls, 2 boys.
4 girls.
4 girls, 1 boy. Or all 5 girls.
4 boys.
Yeah, which means that's probably the most efficient committee, right? Okay, so 3 girls and 2 boys. We already did that already, right? You're going to select out of the 5, 3, and then out of the 4 boys, you're going to select 4. Now what about 4 girls, 1 boy? How many ways can that be done? 5 choose 4, selecting the girls. What about selecting the 1 boy? 4 choose 1. And then what about 5 girls and no boys?
That's 1.
5 choose 5 times 4 choose 0, right? You're selecting 5 girls and then no boys. Now what do I do with these numbers here? You multiply these because they're close together. And then you add these because they're far apart. Well, the real reason is because they're mutually exclusive. So, you write this on your paper, you get 3 out of 4 points. You want the last point, now you got to compute. Now, we already did this, that's 60, right? What about this one? 5 choose 4 is the same thing as 5 choose 1, which is just 5. Anything choose 1 is just anything, right? 4 choose 1 is 4, so 5 times 4? 20. 5 choose 5 is the same thing as 5 choose 0, which is 1. Anything choose 0 is 1, so this is just 1 times 1. 1. Add them and you get 81, and there's your answer. It's pretty easy, yeah? Combinations. You think you're good? Okay, now we do card problems. Now, if you can do card problems, you can pretty much do anything. Because card problems are very difficult. Now, I am assuming that everybody knows cards. Like, you guys know there's 52 cards in a deck. You gotta tell me if you don't know now, because this is gonna be in the test. There's 4 suits. Each suit has 13 cards. Okay, you good, yeah. Okay, so from a standard deck of 52 cards, standard deck, later on I'm gonna throw in the jokers just to screw with you. Okay, but from a standard deck of 52 cards, let's do poker hands then. How many different poker hands are possible? How many cards in a poker hand? 5, the standard poker, right? So, out of these 52 cards, how many ways can you get 5 cards? 52 choose 5. Simple, yeah? Okay, now compute it. 5, 4, 3, 2, 1, under 52 times 51 times 50 times 49 times 48. Let the canceling begin. Dot 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 is 10 goes into that 5 times, 12 goes into that 4 times. So 5 times 4 is 20, times that is 980. What is 52 times 51? Come on.
622.
Well, 50 times 50 is 2,500, right?
Wait.
Oh, yeah, 2,500. Well, duh, you're doing it on your calculator, that's no fun. Anyway, you multiply it all out, you get 2,598,960, I believe. Anyway, special forces, this is a good number to remember. You know why? Well, even the regular citizens, it's good to remember this number because this is always going to be the denominator when you do a poker probability, right? Because this is the total possible hands you can make. So, for example, okay, if you were to randomly just deal a 5-card hand from a standard deck of cards, what's the probability you would get a royal flush? Now, do you guys know the poker hands? Okay, a royal flush is when you get ace, king, queen, jack, 10 of the same suit. Do you know that there's aces and jacks like that? Then how come you don't know royal flush? How are you gonna go to Las Vegas and win money? Okay, so now that you know what a royal flush is, I defined it for you. What if you were to randomly deal a 5-card hand? What's the probability you would get a royal flush? 4 out of this. How come 4? Because you can have ace, king, queen, jack, 10 of spades, that of hearts, that of diamonds, and that of clubs. There's 4 different royal flushes, so it's 4 out of that. Okay, so we can go through. Okay, is royal flush, now this is no wild cards now, is royal flush the highest hand there is?
Yes.
Now, how do you know which hand is higher than the other?
Well, yes, least probability.
Yeah, the smallest probability is the highest.
Yes.
Okay, so there's 4 ways of making a royal flush, so therefore the probability is 4 out of this number here, right? Okay, now what are the other high hands? What do you have? 4 of a kind? Straight flush, which one is higher? 4 of a kind or straight flush?
4
4 of a kind.
Wow.
Yeah.
You don't know. Okay, 4 of a kind. Let's just put it down what you think it is. Then straight flush.
I don't know.
Straight flush.
Flush.
Full house? Or flush?
Full house.
Oh, you guys think you could win. Full house. Flush, then flush. You even know what a flush is?
I thought flush was
Flush
higher.
is 5 cards, all the same suit, like all hearts. All hearts.
No, I thought flush was higher than flop.
Yeah, I think it's straight.
That's a straight. It's called a straight. Oh, so a straight would be like 3, 4, 5, 6, 7, but not all the same suit. Because that would be called a straight flush. It's higher rank.
I thought a flush beats.
I don't know. I'm putting a what.
Look it up.
No, don't look it up. We're gonna figure out the probabilities, and then we'll know what order it's in. Put that thing away. We don't need that thing. Okay, what's below flush then? 3 of a kind? Straight. Straight. 3 of a kind.
2 pair.
2 pair.
Pair.
1 pair.
Ace high.
And then nothing. That's nothing.
Ace high.
Yeah, that's nothing. Okay, now out of these, you know what the hardest one to figure out is? Nothing. Because to compute nothing, you have to compute all of these first, and then subtract it from the 2,598,960.
We don't want to do.
So that's gonna be.
No, that's too difficult for you. Okay, so the higher it is, the easier it is to compute. Okay, so there's 4 royal flushes, right? Everybody agree? Okay, let's do 4 of a kind. Okay, now when you do card problems, again, try to think of a specific case, and then you multiply by the number of cases. That's always a good technique. So do a specific case. 4 aces. Okay, you want to go with aces? Okay,
52.
4 aces. Okay, how many aces are in the deck?
13. 13.
There's 4 aces.
I'm trying to figure out the number. It's 13.
There's 4 aces in the deck. How many ways can I select 4 of them to be in my hand? 4 choose 4, which is 1. But then there's a 5th card. You gotta remember, there's 5 cards in a poker hand.
Okay.
No, that's important. So if you take away the 4 aces, how many other cards are there in the deck? 48. Out of those 48 cards, how many ways can I select one of them to be that 5th card? 48 choose 1, which is 48, right? So this is how many ways you can get 4 aces. That's a specific case, but is that the only 4 of a kind you can get? No, you can get 4 kings, 4 queens, 4 jacks, 4 tens. In fact, you know what? Ace, king, queen, jack, 10, 9, 8, 7, 6, 5, 4, 3, 2. These are called values. So there's 13 values, right? So what do I multiply by? 13, because there's 13 different 4 of a kinds you can have. So you multiply that out and you get 48 times 13, which is 4 carry 2, and then 48, so 4, 2 carry what? 624.
Wait, but you have to reduce this part.
No, I'm not doing probability, I'm just saying how many 4 of a kinds are there.
Oh.
The probability would be that over this. Okay, everybody understand what I did? Okay, we'll just do as many as we can. Okay, you're gonna find that when we get over here, very difficult. Some of you, your brain's gonna explode. Okay, straight flush. Now, what is a straight flush? That's like 3, 4, 5, 6, 7, all of the same suit. But it cannot be ace, king, queen, jack, 10, because that's a royal flush. Okay, now here's another problem. Can you count ace as low? Can you use an ace as a 1? Yes, you can. So, let's do a specific case. Spades. How many straight flushes are there for spades? Just count like this.
I don't know.
1, 2, 3, 4, 5, 6, 7, 8, 9. But you don't count that one because that's a royal flush. You get it? So there's 9 straight flushes with spades. So how many total? Times it by 4, right? Because there's 4 suits, so 36. So, see, a straight flush should be ranked higher than 4 of a kind because it's harder to get. See, you guys think you guys know. You guys don't know. Okay, now, are you ready to get your mind blown? Full house. Okay, let's do a specific case.
3 aces.
3 aces and 2 kings. Okay, that's what a full house is. 3 of one kind and 2 of another. Okay, specifically, how many aces are there in the deck? How many ways can I pick 3 of them to be in my hand? 4, choose 3. How many kings are in the deck? 4. 4, choose 2. Okay, that's how many ways I can get a full house of 3 aces and 2 kings. Okay, but now we're going to multiply it by the number of cases. 13 times 12 or 13 choose 2? Okay, look at these. Look at, you have 13 values here. Take away the ace here. You have 13 values here. How many ways can I select 2 of them to be the 2 things here? Like you can pick ace and king, king and 6, 10 and 3, 8 and 5, queen and 6, 9 and 2. How many different ways can you pick that? 13, choose 2. That's right.
Wait, wouldn't the order matter? 'Cause
Exactly. Okay. Okay. And that's the thing that's gonna blow your mind. Because once you pick the 2, like say you pick the ace and the king, you could have 3 aces and 2 kings, but couldn't you also have 3 kings and 2 aces? So that's why you gotta multiply by 2, which is the same thing as the 13 times 12. See, there's all these things you gotta think about. Okay, now how much time do we have? Well, forget about multiplying it out and getting the answer. No, let's do it. 4 times, what is 4 choose 2? 4 times 3 over 2 times 1, 6. What is 13 choose 2? 13 times 12 over 2 times 1. That's 13 times 6, 78 times 2. So that would just be 78 times 48, right? 4 carry 6. 2 carry 3. So that's 4, 4, 7, 3. 3, 7, 4, 4. And that's why a 4 of a kind is higher than a full house. This is easy to get. Okay, we're not going to have time to do all of these. Let's just do one more. One more. Pick one.
Nothing.
No, I told you. The only way you can get nothing is you got to add all of these up and subtract it from 2,598,960. That's the only way.
2 pair.
Okay, let's do one pair. Okay, prepare yourself for mind blowing right here. Okay, do a specific case. A pair of twos. Okay, but you gotta remember now, these last 3 cards cannot pair up now. Right? That's the hard part. You gotta make sure they don't pair up. And 4 twos is not a pair of 2s now. So these 3 other cards cannot pair up, and they can't be another 2 in there. You get it? Okay, well that's what I'm going to show you. Okay, how many 2s are in the deck?
4.
How many ways can I pick 2 of them to be in the hand? Okay, that's easy enough. Okay, but now these 3 cards. Once you eliminate the 2, now you want these 3 to be all different, right? So of these remaining 12 values, how many ways can I select 3 of them? 12, choose 3. You get it? Because they have to be different. They cannot be like 2 4s. So out of these 12 remaining values, how many ways can you pick 3 of them? Okay, now, once you pick the 3 of them, let's say you pick the 5, the 8, and the jack. There, how many 5s are in the deck? How many ways can I pick 1 of them to be in the hand? 4, choose 1. And then what about the 8? 4, choose 1. What about the jack? 4, choose 1. There you go. You guys understand that? Because you got to make sure these 3 cards do not pair up. They have to be all different. And that's your answer right there. Yes.
Oh, wait, so if you throw in the jokers, how is that affect on
Well, if you throw in 2 jokers, then
It can be anything.
no, because now, okay, like for example, 4 of a kind. Like, how can you get 4 aces? You could get like 4 real aces and another card, or you could get 3 aces, a joker, and another card, or you could get 2 aces, 2 jokers, and another card. Then what you would have to do is you got to make cases. Isn't this fun? This is fun. This is the funnest thing we've done so far. Okay, but luckily for you, I'm not gonna give you poker hands because it's pretty difficult. But you guys got to be able to do the basic problems like committees with people and stuff like that. Okay, the bell's gonna ring in 3 minutes. So is your mind sore? Your brain sore?
Wait, Mr. Park, if you're in the jokers, you can put
Yeah. But then you got to make cases because how can you get 5 of a kind? You could have 4 aces and 1 joker, or you could have 2 aces and 2 jokers. So you gotta split it up into all the different cases. Yeah, and then this total is going to be different, right? It's going to be 54 choose 5. Joker is wild card. It could be anything you want it to be. Wait, come on, you gotta know that at least. Anyway, since we're only gonna, we might not even have a practice test to do, I'm gonna dumb down the test. Cause usually I put like 3 or 4 problems where you gotta think,
Yeah, but like negative field switching.
but I won't put those.
Therefore, it's still,
You just,
because as long as it's a
wait, what?
these
Okay.
four, it would.
The Kobe rule is.
Oh,